Nobody has seen a wormhole. Nobody has produced one. Nobody knows if it is just a beautiful math, but without a physical reality.
Well, we'll take the world's best quantum computer and see if we can map that into building a wormhole.
And then it became just at the edge of what's possible.
I think the discovery of the Higgs, which came about 10 years ago, was up to that point the most exciting point of my entire career. This, to me, is equally exciting.
It can begin to explore quantum states that are very hard to realize in nature directly.
Now the wormhole becomes traversable. It opens. You really can go through. So the story begins in 1935 when Einstein wrote a paper with Rosen where the first time Einstein-Rosen bridges appear. And these are bridges that connect two seemingly unconnectable pieces of space-time.
ER, Einstein and Rosen, they pointed out that solutions to general relativity allowed for two black holes, which are connected, but with a kind of bridge, what we call a wormhole. But that wormhole has the property of being non-traversable.
Wormhole is a very unstable passage. It opens and it closes and it gets chaotic and it gets destroyed very fast.
So Einstein, when he proposed the wormhole, he was very frustrated because you couldn't actually go through a wormhole, and he was able to realize that himself. And so what good is a wormhole if you can't put anything through it? And it turns out that's because he wasn't putting in the quantum physics.
1935, same year, another paper, the EPR paper, which is Einstein, Rosen, Podolsky.
EPR is about quantum entanglement and what Einstein called spooky action at a distance, something he was not happy with.
Entanglement is this property that subatomic particles, they are partners. Even if you take them apart and take them at the other edge of the universe, they hold information that if you measure the one, you know what the other will be. So entanglement is a strong correlation.
Einstein didn't like quantum mechanics, and this made it very challenging for him to understand how to reconcile quantum physics and gravitational physics. Physicists want to understand as much as they can about how the universe works, so it has been a challenge which has occupied many scientists over decades to understand better how quantum physics and general relativity fit together into a coherent picture.
Einstein's dream was to figure out how to connect them.
Those two papers, there was no reason to think at the time or for decades afterward that they had anything to do with one another apart from there being some authors in common.
And then comes 2013, Maldacena and Lenny Susskind. They say ER equals EPR. They are the same. This is very daring.
Wormholes and entanglement are the same thing. That was totally unexpected. One of them has to do with general relativity. One of them has to do with quantum mechanics. Didn't seem like they had anything to do with each other.
A lot of times in physics, you can have two different descriptions of the same thing, but it's just sort of a remapping of the same physics. And we call that a duality.
The basic idea was that when you have quantum entanglement between two black holes, necessarily there will be a wormhole connecting them.
It's like saying gravity equals quantum mechanics, if we want to say it in a simplified way. So there we have a picture of quantum gravity.
We have this dictionary that relates gravitational phenomena to ordinary quantum physics.
You can tackle the same physics from these two different angles, and that's the most concrete paths forward we have in building a full theory of quantum gravity.
The physics of the black holes, we think is physics of quantum gravity, but we cannot send an experiment in a black hole and validate that.
So instead, we can ask, can there be quantum systems whose dual description looks like wormholes? I think it might have actually been during a talk by Juan Malmacena about dr equals EPR that I started to wonder to myself, could traversable wormholes exist, right? And people thought it was fascinating as an exotic configuration of space-time, but I think many people probably suspected that it couldn't work. So we saw that it could.
One of the magical things about quantum mechanics is you can actually have negative energy, and this allows you to do things that you would have thought otherwise were impossible.
What Daniel Jaffrus showed was that if you introduce what's known as a negative energy shock wave, you can support your wormhole and get something from one end and have it come out the other.
Now I'm an experimentalist, so I look at that and I do, all right, what can I do about that?
We were thinking, we have the ability to do things in quantum in the laboratory. We're physicists. So could we imagine actually doing something with wormholes? It almost occurred to us immediately that we should be using the best quantum system that we know how to manipulate. And what is that? It's a quantum computer.
Quantum computers speak a different language than the ordinary language of bits. A bit, you look at it, okay, it's a 0 or 1, that's it. The correlations among qubits are richer and a lot more interesting than correlations among bits. It's this language of quantum entanglement. And so there's a world out there, this extravagant quantum world, which we just haven't been able to explore.
I've worked on a few projects at Google Quantum and got to know the device a bit. And the Google device is the best quantum computer that is around. All the magic happens in this little chip. You have the actual qubits as these superconducting pieces of aluminum, and that's where the entanglement happens. We had the access to the Google quantum computer. I came over with Maria and Daniel and Joe, and we were like, we have a proposal to try to, observe a wormhole on the quantum computer.
And to put the proposal together, it was obvious these are the people.
In physics, you have to have the courage of your own convictions, and you say, well, maybe it won't work the way that I thought, but we'll learn something by trying. And that's really the attitude we had going into this. I don't think we really thought it was going to work, but we thought we would learn a lot by seeing how far you could get.
They didn't say, you're crazy, let's do something else. They said, okay, you're crazy, let's do it.
You can use the holographic duality to create the quantum version of the system. We look instead at this set of entangled qubits, and we evolve it in a way that has exactly the same physics as the gravitational wormhole. And so on the quantum computer, we can directly send a qubit from one side of the wormhole and watch it come out the other. If you take the physical system that theoretical physicists say, this is a wormhole, and you work out pencil and paper, so how good of a quantum computer do I need? You get an answer that's like a quantum computer 10 years from now. It looks hopeless.
But we thought, let's try.
All right.
So we are here in our GQ2 lab, and then the controlled signals actually are produced in these racks sitting next to the cryostat.
When you try to just run a wormhole as the theorists have prepared it on a quantum computer, you find that you need to implement this very large system.
So that's big. That's a big, fat problem. I cannot put it on an experiment.
And so what we have to do is we have to do what physicists call coarse graining. So you want to preserve certain features, in this case gravitational features, while throwing away all the unnecessary components. We knew we needed to go to a smaller system size, and so we were kind of banging our head against it for a year or something. And then finally you come up with a weird idea that might work. The idea of rewriting it as a neural network is something that's kind of out there, and that's like it's a weird idea because you usually don't think of physical wormholes as neural networks. The wormhole itself that has like these many parameters that we treat as neural network weights. We then have a data set that we're going to train on, which is the dynamics that we want to observe that correspond to a wormhole. So it sounds like a generic machine learning problem now, and we can just like plug it straight into the machine learning toolbox. I proposed the idea and tried it out. The original system has 210 terms. The machine learning managed to keep all this intact while making a much smaller system.
It's still baby enough that it fits on the crib.
That was the kind of first moment where like, it might be possible, you know? this whole wormhole thing we've been talking about for 2 years, like maybe we can actually do it. At probably like 2 in the morning, I was running these quantum circuits. We're looking for a peak. That's the qubit making it through the wormhole. I'm watching the data as it comes out. There's a little bit of a noisy peak. At first, I was like, this is probably just noise artifact. But as the data kept coming and the peak kept getting clearer, it was like, this is a wormhole. I think I just saw one. And so I was immediately like sending it off to Maria and the others. Like, I think we have a wormhole, guys.
He said, it's there. I said, no kidding, he's there. It was nuts. It was nuts.
What happens is
The qubits of the Google quantum computer are making a little bit of extra space, and that's our wormhole.
a pulse of negative energy falls into the wormhole.
Now the wormhole becomes traversable. It opens.
You put a qubit through one side of the wormhole.
The qubit is now in the interior of this wormhole.
That information will actually spread over the entire quantum system. This spread of quantum information,
It becomes shared by many particles in the form of quantum entanglement. And then, rather remarkably,
it has to refocus as a single qubit. And then, as the wormhole is closing, the qubit is exiting.
I was absolutely astounded. I thought we would get maybe a few steps towards a real wormhole and a real quantum computer. And I never really believed that we'd get all the way to something that was real.
The experimentalists have like reactions that they want to hug the machine. I told my brother in Greece on the phone, and he squealed, and he said, "Are you destroying the world? What are you doing?" And it was difficult to explain to him that nobody is in danger from this wormhole. On the processor, if we had a quantum-sensitive eye and looked in there, we wouldn't see a ripple of space-time. We would see the physics that we expect from the gravity point of view and from the quantum point of view. So if that is the case, then we're making contact between quantum and gravity.
That's been the holy grail of my whole career, is to understand quantum gravity and the things that go with it, like wormholes. We are studying quantum gravity literally from the ground up.
Einstein committed his life to arrive to some understanding of quantum gravity. Here we are, almost a century later. I wish he was alive to see this, because I would like to know what he would say.
Well, what Einstein has said, he would have said ER equals EPR. I told you, I knew that in 1935. But he didn't.
I think this is concrete experimental evidence for ER equals EPR.
The vector is pointing right from the experimental point of view.
This is a confirmation, a direct exploration of this connection between quantum entanglement on the one hand and the way space is knit together and holds itself together.
as Google builds more and more capable quantum computers, we will eventually be able to get this into a regime where we don't even know how to predict what's going to happen. And I think we're going to have hundreds of my fellow physicists now writing papers about all the other things you can think about doing now that we've sort of got this door a little bit open.
And as always in physics, when you are able to explore a new frontier, there will be discoveries that weren't anticipated. Just like when you build a more powerful accelerator to study particle collisions or a more powerful telescope to look at the more distant universe, a more powerful quantum computer will be able to study highly entangled matter that we've never been able to look at before.
I think in the next 20 years, there are going to be a lot of fun for fundamental physics. Being very close with quantum, we're going to learn a lot.
There's so many questions that one could explore using these ideas. And I think most exciting are the questions that we can't yet pose.